shapes are sized depending on the age of the classrooms that go into them. And each of the classrooms is framed like a house. So the shape internal to that extrusion defines the interior so that you can actually feel as though you are always coming to your own home room, your own house, your own figure, a place that will be your classroom for the year. The outside was built with trees native trees from Arkansas, and the classrooms themselves were defined by the tree itself. So we really wanted to be able to fold all these together into the same piece. Notice that windows are not at adult height, they're at kids' height. That house shape, wrapped in wool, is carried on into the inside. It also drops the acoustics, drops the sense of scale, brings that scale down to the scale of kids. And then the view is to the outside. So the outside has this great view because what you want is the outside space, which is also secured, is outdoor air. So a good third of the classroom is fully outdoors for water, for mess, and all the stuff that you can't do on an interior condition. Right? The playscapes maintain that, so you see your house shape and you know which classroom to go back into as your space, all done through kind of section and figure. But ultimately, I'm talking about the architecture. The goal is to really animate and provide a kind of life for these kids who are going to be here. Some of them a couple hours, some of them for the full day. So what you have to really pay attention to is not just the shape and figure, but the material conditions. Because the developmental process of a very young infant through the time they would leave the building is when growth of the brain occurs. It's also when kids are most susceptible to the chemicals that are in our materials. Right? And it comes before birth and carries on through. And that comes in multiple different ways into a child. Right? So as we're designing this project, we're like, how do we design this building so it's a home away from home, but one that's really healthy? One where the materials are actually essential to growth and development, which is the purpose of the building. So we partner with the Healthy Materials Lab at Parsons, which is an advocacy research and think tank for advocating for materials and the health of materials, who itself have partnered with the Green Science Policy Institute to identify 6 classes of chemicals we need to remove from the building environment, particularly when it's with kids. And these include highly fluorinated chemicals, antimicrobials, flame retardants, bisphenols, phthalates, solvents, and certain metals. 6 classes of chemicals. We need to do that not just in the design phase, but in the construction manuals, going to the contractor, and into the operations manual afterwards for the cleaning products. This needed to then also go into the primary surfaces that kids are going to be rubbing up against, putting in their mouths, right, crawling around, right, as well as all the classroom supplies. So the Healthy Materials Lab were to develop an entire classroom supply kit, toys, etc., so that we didn't have plastic toys. The Legos are not plastic. Right? You can't use plastic because of the phthalates, the softening agents, and the chemicals that are in them for kids. This extends into what you put into the kitchen. Right? So the kitchen has to be removed all plastic, all styrofoam, stainless steel, and silicone only for cooking and for eating. Right? Because this is what people are bringing into their bodies and having long-term implications on human health. On the outside, you need to have a growing garden so you understood where plants are coming from and herbs are coming from. This was a research project in part. It's also a very real project. Research in the sense we wanted to set a model for other early childhood education centers to adopt this, adopt the protocols of broader healthy materials, as well as to demonstrate that and to talk about it. The book, returning to the question of section, has gotten printed in 7 languages that we know of. There are a couple of legal ones we've heard about, but not allowed to show us. So the next question is, what do we do? Do we do manual of section part 2? Or do we look at the examination of the materials that we're working on and draw much more attention to that, particularly by planning out the kind of questions not only of the health consequences, but the climate consequences of the materials we choose. This book, I think, is equally, if not more important than the manual section. It's Manual of Biogenic House sections. Right? It's focused around 9 materials, but I'm going to begin with the last thing before I return to the materials. Because as you probably have heard, the most sustainable building you can build is the one that's already built. Right? It's the one that you're reusing the materials that are there. And we've been lucky in our practice to be able to do that and have that challenge of working in an existing space or against another building as a condition for the invention. I think it's really imperative to be able to set that as a kind of challenge, not as something that is seen as of less order in terms of the quality of the buildings. So it's the reuse that is first and foremost. How do you take on buildings that are already there? So if a client comes to you and says, I got a building that I'd like to take it down, your first question is, why do you have to take it down? Can we reuse this? Let's look at this critically. What about it is not so good? Because the climate, the amount of carbon in that building is probably worth saving. Right? It also is about our history. So this is a project that we've had an opportunity to do 2 versions of design and changes for, which is at the Contemporary in Austin. And we very much see ourselves as architects that are adding to the history that's already there. That has had a history being a theater and then a clothing store and now a center for art. Our work is then conceived of as not a wholesale rewrite, but a tactical insertion, which is also tied to the question of budget. So you're tactically changing the large window for display for the department store into the backdrop for the picture screen. You're now walking into the front door through an anamorphically distorted sign called Art House. The staircase is the piece that we want to draw daylight into this existing space because it was more of a solid box. But in order to do that, we wanted to make this do more than just one thing. It just didn't want to be a staircase, didn't want to be just a skylight, so that where you get your ticket is the first step of wood to go into the main piano nobile, which is where the galleries are up above. The slope of that step is derived, and the angle going all the way up to the skylight of the side piece is set by the angle required by the tip of the nosing by code. In other words, your angle for your rise run is derived and carried out into the overall building itself. We had an opportunity to add this, so we put a rooftop addition onto it to be able to transform it to add one more outdoor story so that it could be also used for public and social events. So it becomes a beacon to the community as well as a gathering point. One of the key things you think that architecture has to do in the digital age is to gather people together to be able to talk face to face. Another project in New York City was a kind of interesting challenge where we had a full through block, 200 plus feet long building to transform into museums for posters. Now, poster is an art form that's supposed to be on the street, right? It's the art form that you put it up, you slap it up on the street. So how do we actually pull the street into a building that is fully embedded in the block in New York City? So that's the challenge. Right? And this is what it looked like before. So if this is the length of it with a series of columns going down the middle, what do you do with this existing condition to transform it to meet the conditions of being a museum for the display of posters? First thing is to actually pull that street in, make that division between public and private or gallery, run right through the middle of the building, do a series of studies. These are done very quickly over digital massing by hand. Tweak this so that you can get the right weights of where you want spaces, and then carry out a canopy so that it really reinforces the idea that you're walking within a street, even though you're inside. Provide a secondary entrance on the back side, then insert an armature of bamboo and wood on one side that would be all the amenities, services, gift shop, etc., and then provide the gallery on the other side and more support spaces on the lower floor with a connection through the wood and bamboo. section and model demonstrating this idea of trying to turn the entire building 90 degrees, pull the street in. So from the outside, you get a hint of where that is, but it's really on the inside that you see this bifurcation. This isn't Photoshop, right? This is, on one hand, is milk paint, or sort of it's a milk plaster, and on the left is the wood and the dividing line between the two. That carries your eye, pushes it back, so the entrance to the gallery is on line with the line that's going right up the middle of the building into the entrance, into the gallery, making it feel as though you are literally walking in a sidewalk street. Showing and revealing the original columns, and those columns then are maintained on the thermally controlled interior where we have fragile artwork that used to be displayed on the street is now being showed within a gallery setting. And then really calling attention to the sort of intersection between the new and the old as part of working in reuse. Right. More recently, we've been really interested in bio-based building materials, in part coming out of the research that went into Manual of Biogenic Health sections. It's also been played out in a series of research projects that I'll focus the rest of the lecture on. And this is really, I need to set this up in a way that you understand the consequences and, more importantly, the agency that you all should have as architecture students in addressing our contemporary challenge. There's no question, this is without scientific debate, that global temperatures are going up. It is having dire consequences to our health, to the planet, to what we live in. This is a photograph of the Canadian wildfires taken from the top of a skyscraper in New York City. It's not Photoshop. Challenge, and this is playing out, and you'll always see the reference to data, and we'll write this from Architecture 2030 and other data sources. Right? That we need to basically change the way in which we're dealing with the amount of carbon we're putting into the atmosphere. Right? You've probably heard this before. Our current policies have us anticipated by the end of this century pushing average global temperatures up close to 4.5 degrees Celsius. Right? Average temperatures. So if you think it's hot when it's 100 degrees, try 125. So what are we going to do? If we want to keep the amount of global temperature down low enough, we have to reduce the amount of carbon we're putting into the atmosphere. Projected in 2020, the argument was by 2030, we have to reduce globally, by the way, all CO2 by 65% to maintain a living chance of keeping below 1.5 degrees Celsius at the global temperature. Right? Well, we had COVID, dropped a little bit, and then came back up again. So this is where we're at. Right? At 2025, we have a lot of work to do to be able to get a 65% reduction with a higher probability of keeping it below 1.5. Right? So what does this have to do with buildings? Right? This isn't. If you look at the pie chart with buildings, I'm giving a lecture on architecture. I'm really interested in section. I'm interested in form. I'm interested in the light of architecture. What does this have to do with architecture? Well, operational heating, cooling, lighting of buildings in the global amount of carbon released is 28%. That's just heating and cooling buildings, a substantial amount, right? So we should focus upon that. And we have insulating buildings, going all electric, net zero, etc. There's this other one, which is up here, which is the embodied carbon. Right? Embodied carbon is the amount of energy that goes in the CO2 equivalent that is released in the making of the buildings, not the running of it, the making of the buildings. But that's less, right? So you look at this and you're like, oh, I'll focus on the operational energy. And that's mostly where the discipline has been focused for the last 40 years, since 1973. Here's the challenge. If you take a new building that's built today in relatively modest energy code of 2020, about half of the energy over 30 years, or CO2, will be related to the operation, and half will be related to the materials. So you're like splitting it 50-50, right? Well, if that building becomes energy efficient, majority over the 30 years is in the materials you put into the building. Here's the other thing, and this is why it's imperative, which is why it's in the title today. This has to do with over time. When you open that building, it's released. You're not getting it back. It's in the atmosphere. But the energy system can go all electric. It can go solar. You can change the operation. And so that's released over time. And you can change it. We need to reduce the amount of carbon now. So where are you going to have it? Over the operation or over the material choices that you're making as students and as practitioners? If you're faced with this, it's very hard to be able to go and use conventional building materials. Right? So that's over time. We got time issues. We also have the sheer amount of construction. You're like, oh, I got the answer. Don't build anymore, right? Just don't build anymore. You know, you'll all be out of job. Oh, you do renovations, right? Here's the challenge. You look at the amount of floor area projected globally, 2.5 trillion square feet globally is going to be built. What's that going to be built out of, right? What's that going to be built out of? That is the equivalent of building all of New York City every 35 days for the next 40 years, to give you a sense of scale. All right? The other challenge, and we've been talking mostly about carbon, and that's climate change. And this is from the Stockholm Resiliency Center. Carbon's only one of 9 planetary boundaries. We're exceeding all but 3 of them right now. And that has happened pretty close to in your lifetimes. Why? Why is that the case? Why are we changing the way in which we're building? I mean, our environment comes through the way in which we build. We need to move from the legacy, and this is my polemic to all of you. We need to move from a legacy of modernism, concrete, steel, and glass, carbon intensive, it's linear, it's extractive, it's global, right? In which you ignore some of the environmental and health impacts, to effectively a biogenic and geogenic material, one that's regenerative, where the materials have the capacity to replace, where they're low carbon, if not carbon sequestering. It's local, it's healthy, and that this is a new paradigm for design. Right? It's no longer the continuation of a practice of modernism or the aesthetic of modernism. Right? What does this mean? Well, it means looking very closely at the materials, the embodied carbon. Very simply, and this is in the book, in the appendix, if you're looking at buildings that are materials that are emitting, use less of it. Maximize the use of materials that are carbon sequestering. Very simply, carbon sequestering materials are the ones that are built through photosynthesis, otherwise known as plants. Manual of Plants section wasn't going to be a good book title, so we chose Biogenic. Just the challenge, just to give you a sense of the scale. Concrete is responsible for 7% of global climate CO2, and that's the chemical process of the burning of limestone. Same thing with steel, right? You can't get away with it with a better energy source. It's a chemical process of the fabrication of those materials. Construction industry is 38%. 38%. Do you know how much the airline industry is? I flew by a plane here. Right? So you think it's probably 12, 15, those damn planes. So that's both a question of like, oh, what do we do? But also I think about it as, oh my goodness, look at this agency. This is the opportunity to make change, to really transform. Look at the scale that we're talking about here. So what do we do? It's the other challenge of the chemical process. Global chemical use is expected to double between 2019 and 2030. The building industry consumes more than a quarter of that. If you look at the history of materials, up until World War II, almost all materials were organic. It's only after World War II, the introduction of chemicals, polymers, biocides, flame retardants, etc., you have a transformation in the material practices of architecture, material practice of interior design, right? And this growth is in polymer materials. So the question is, well, these chemicals, they must be protected. Someone must be observing them and looking at them really carefully, right, to determine whether they're good for kids or good for all of you. Of the 85,000 chemicals in 1976, 62,000 were grandfathered, of which only 250 have been properly tested. Okay? So if you're choosing to use a building material, how do you know it's healthy? You probably don't, unless it has a declare label on it, unless it had third-party certification, right? You have exposure for the entire process. I'm not just talking about when the building gets open, but who extracted the material, who processed it, where it was impacted, all the way down the life stream, and then into its end of life. Right? What are the possible long-term impacts? Again, I've looked at the Healthy Materials Lab for this information. So this is what was motivating the book. It's both about carbon. It's also about material health. Like, what are we putting into the world as architects? Right? What do we make? What is our role to make meaningful change? So Manual Biogenic House section chose to use the house. In part, there's a couple reasons. A house has been a site of invention. It's a small figure. It's a place for testing and experimentation. It's pretty ubiquitous, particularly in the American context, right? So the capacity to make decisions about houses is something that most of you in the room will at one point have a chance to do, right? It's also a huge emitter of carbon. The amount of carbon produced in annual house construction in the United States is equivalent to the annual emissions of Sweden. To give you a context. Why is that? Well, standard American house was 1,000 square feet in 1950. Any guesses as to what it is now? You can kind of guess from the graphic, right? All right.
3,000.
3,000, pretty close. The number of kids have dropped. The number of cars have gone up. Right? What's this made out of? Other than the timber or wood that went into the platform framing, it's almost all polymers. It's almost all polymers. Right? Most of what you see in this image is a polymer. The wood siding, not wood siding. Okay. The wood columns, the wood shutters. Shall I keep going? That's not unique to the exterior. It's also the same on the interior. The luxury vinyl floor. Right? Nearly everything in that image, except for maybe the wood veneer, is a polymer. All right, with chemicals in order to make it. Right? Where does this go then? So you have to look at where it comes from to then figure out where it goes. If it can't be recycled or reused, almost all of it after 65 years goes into dumpsters. Your typical American house lasts for about 65 years. Right? So the question is, how do we make this change? Because we're actually contributing. And don't worry, I'll get to the happier news, because I see a lot of your faces like, oh, God, you're like dumping on us. All right? So where did most of the plastic in the ocean come from? What's the primary source of plastics that go into the ocean now? Microplastics in particular. Anyone know?
Textiles?
Textiles? Some textiles, yeah.
Water.
Where?
Plastic water.
Plastic bottles break down. Yep. Plastic bottles break down. But here's the issue. More than 50% comes from paint. Comes from the paint you put on buildings. Comes from the paint that are on ships. It breaks down very quickly. Most paint is plastic. Most paint is an acrylic byproduct. Right? It looks like this. Then goes into your body with effects that are still being studied. But just to give you a sense of the scale of this, based upon a recent report at the University of New Mexico, all of you have about a weight of a spoon plastic in your brains right now. Right. So as you make your buildings and design your buildings and manage them, you're going to be eating that. Right. So you have a choice over what. You can also scan the QR code. I just want to make sure that this is all backed up, is factually supported by scientific evidence. So when I look at this, I'm looking like, how do I make real meaningful change? And more importantly, how do I address one of the fundamental problems? And it's a problem not just for materials, but it's also a problem for the legal practice of architecture, which is we basically build buildings out of multiple layers, each doing one thing that are hygienic, separating the interior from the exterior, and each of them is backed by a different legal counsel. Right? So each thing only does one thing. Right? The paint only does one thing. The vinyl only does one thing. The gypsum wallboard, the thermal insulation, they are all isolated. Can we think about buildings not as isolations, but actually monolithic materials in which one material can not only be healthier, but actually can do more of these things better? And that is when you start getting really excited about the possibility of bio-based building materials, in which earth-based building materials or cork-based building materials not just perform better, but they actually change the way in which you think about what a building can be, because it's no longer about multiple layers, right? And this returns us back to this material that informs the book about biogenic buildings. Each of the chapters is organized not by section type, but by material. And in this case, looking at very clearly where are we going to have the greatest impact in these materials. And that goes to growth cycles. Right? If you want to make impact now, which would you choose? The plant material that's going to take 30 years, or the plant material that takes 0.2 or 0.3 to grow? Right? Because it's time is a critical issue in terms of growth cycles and broader carbon issues. So it's that informed condition. We're also excited to be able to show not just what the materials are, how they're grown, how their broader cycles, from growth cycles, construction cycle, and then how it returns. Because if you can't close the loop, you're adding to the waste stream. But give a kind of overview of how these materials are harvested, how they're grown, how they're processed, what are the materials that are produced out of them that become the capacity for houses or architecture. So all the chapters of the house are based upon this. The books are based upon these material chapters. 55 houses drawn from around the world, all built, all exceptional in terms of their capacity to delight. So this isn't about thinking about the future. This is about what can be done now through these materials. Timber-based building located in Brazil, different climatic condition. Right? And then the one-point section perspective to show the intersection between the material and the experience. Right? In parallel, we've been doing a series of drawings and representations trying to explore for ourselves what the hybridization of different materials might be and how those can inform a different way of thinking about architectural form using the house as a figure. So in this case, looking very carefully from our standpoint at straw. I'm going to give you a quick understanding of why straw. Straw has two different growth cycles. It's a waste crop, namely barley, rice, wheat, all the things that are harvested as food. The stalk that's cut off is often burned. It's not used for bedding. It's not a food anymore. Most of that goes back into the carbon cycle. If you capture it, store it in a building, and were to capture all of the straw globally, that alone will offset all of the carbon emissions from the entire country of India in 1 year. That's the amount that's sitting out there to work with. But it comes in very different forms. It's got a quick harvest cycle. You don't have to replace other food crops. So you don't have to choose between food and carbon sequestering building. It's the same system. It's low-hanging fruit. It already is typically done by baling or stuffing and then putting plaster on it, right, to build as a building. So here are your pails. Here's your plaster system, right? It's also used as thatch, but that's slightly different than straw. And I'll get to that. There are buildings out there using jumbo bales that are spectacular, right? That have this amazing ability. These are really, really big bales, not the small ones like the jumbo bales you've seen. Right? Capacity to produce a kind of corbelled ziggurat-like house form, all out of this one material, clad on the inside, clad on the outside, that is thermally modified. It passes moisture. It's resistant to rot. In a compressed form, it does not burn. It also sequesters in that one house a huge amount of carbon and is captured into that building. Right? This is our own proposal using the same idea of how can we use the idea of jumbo bales to drive architectural form. This isn't designing something and sticking the material in, it's deriving from the material. So we're looking at the intersection between CLT as a kind of weight to be able to compress the jumbo baled straw and use the jumbo bale to maximize the amount of mass in a building. It's almost the antithesis of modernism, which was driving towards thinness. We're actually interested in driving to thickness. So at the top here, essentially understanding jumbo bales dropped into place with CLT modules dropped on top of them, then a panelized sun or a skylight above it that then produces a kind of series of figures of inhabitable space. In other words, what we're interested in doing is producing a section that would be effectively low sun steroids. From the inside, having that paradox between something that's super thick and at the same time really transparent. Right? That kind of juxtaposition between these different capacities that are often seen as oppositional. Right? We're also interested in how we can use the circular jumbo bales, right, to not only define space, but to think about them if they are clad with an Intello system or wrapped with wood battens to reimagine and revisit early childhood education centers. Instead of doing something out of a more conventional building, what if we actually made this out of jumbo bales, using essentially a ring beam over a series of circular straw bales to drive the classroom form. That classroom form then has a skylight in the middle that then has this sort of sense of being in this kind of really solid world that would be supported by CLT exterior-based modules for the water and plumbing, creating effectively a process that drives a very different form for an early childhood education center, extending out into the playscapes. And of course, if we did one out of circular jumbo bales, we'd have to do one out of rectangular, and it generates a very different form. Right? So that interplay between form and material is kind of the essential to the unexpected play that comes out. We've been doing a couple other research projects. One is trying to figure out how we can compress straw to make a kind of building block. Is that possible? In other words, can you make a compressed straw system? And so we built our own compression machine, because if you can compress straw, you reduce the amount of air, you basically make it so that it doesn't light on fire, it doesn't have the capacity of it to have any essentially rodents go into it. It also means that it can, if you compress it tight enough, can take structure without having a wood framework around it. Right? So this is the goal of this research, to try to identify if we could compress straw, combine it with a series of different binders. And this is my brother mixing it thing with lime to do wood glue, lime, earth, cement, other kinds of lime, and mycelium to get the binder to work. And they had limited success, but it still didn't produce the kind of condition we were interested in. This is just pure compression rates at different conditions that provide different structural capacities for the project, for the material. And then, of course, you have to take a chainsaw to it just to see if you can make space out of this mass. What we realized is that, that material research led us to two very different products that are already existing in the market. One that's designed for this intent, the other one we're adopting and reinventing for two projects that are currently active in the office. One is a house that's been filed through code appropriately gone through. The other one is a research project that's called the Old Straw House. And the house, this one is basically a straw wall cassette-based system that for a house on a lake that's for a client that has lifted up off of the ground, so not putting any concrete in the ground to the extent possible, and then building it from prefabricated panels that can be dropped into the site because of the nature of the site. The wall system is compressed straw. The floor is timber HP. It's filled with essentially a timber fill. It's an all-wood system. Uniquely using lime plaster as the air barrier on the inside, right? This is the work that we're working on with New Frameworks out of Vermont. They're the ones manufacturing the straw panels, right? And the straw panels come with fully engineered systems, already pre-kitted together. And this is the factory that is built in. And New Frameworks moved into this kind of construction because they realized that it's better for them to build under cover with straw than to try to do it outside. They also produce a working condition for their workers that's much better than being out in the field, right? And the best part about this is the amount of capital needed to do it. It's not a hugely capital-intensive process, right? So they are running an educational shop for trying to get other startups to use this building system around the country, right? Because it captures so much straw and is such a smart building system. And this is Najat, who's the lead panel designer, demonstrating to us on our tour how this thing gets compressed to be able to meet the compression layers, how it then gets skinned with lime plaster in a controlled environment, and then in this case brought out for temporary storage before it goes onto the site. This is from 2 weeks ago, where we're using helical piles to drive into the ground so we're not having to drop concrete, so we can lift up off of the ground and allow air to move around the entire house as opposed to deal with the kind of water issues you get when you put something in on a hillside slope. One person, one machine, one helical piles in 2 days. At the end of life, this can be screwed back out. This is the second project, a more experimental project that my brother has been running through a grant at Princeton University. And it's trying to use, in our research, trying to make a kind of compressed straw panel, we came across something called DuraPanel out of Australia. And DuraPanel is typically used as a sheet good, very large sheet good, as you see in the lower right, that clad ceilings for large spaces. We're interested in saying, have you ever used it as a wall? Not with the structure around it, but just as the wall. They're like, no. So we got them to send a container of it so we could experiment with it and look at the kind of compression rates and realize that it actually has a linear load to position compression, which is really good because you can then map along that piece, right? So we did full compression tests, analyzing how that ends up working. You see it happening upper left or in the right, bending. That one's a bending test to be able to really figure out if this straw, which is just straw that's been felted under heat so that the lignin in the straw is its own binder, and then wrap with craft paper to hold it together. So it's just straw. Right? You can't burn it because it's so compressed. There's no air in there. Right? So we now have a material that if we can cut it into strips, can become a stacked structural material. The other project on the lake had used the wood as the structure. It was vile. It was put forward. We had to demonstrate that it was going to be structurally stable by contemporary building codes. This is an experimental one. We're looking to figure out, can we make this not only prefab the system, stack it so that the straw is here, and that's the structural loading, and put thatch on the outside as your primary rain barrier, right? In a form that's big enough to start getting at issues of compression, right? And one that's unusual, that comes out of the logic of the material itself, right? It's not a form we're inventing, it's a form that comes out of working with the material. Right? Testing to make sure where the compressions are going to be, what the creep will be, as well as looking at the kind of interior environment for this experimental demonstration of the performance capacities of an all straw building. Straw on the outside, straw on the inside. It's put together with wood pneumatic nails that are powered in so that if you have to take it apart, you don't have to worry about having steel in there. There's some steel rods that go through to tie it together, but it's primarily put together with the friction of the lignin, which is basically the glue of the wood cell as it goes through the straw. Made as a module because we have to be able to get it up to the site, wrapping it for weather along the way. Then got thatch to be able to do the outside and made those as well with all of it with the student researchers to be able to develop a prefab series of components that can be clipped onto the outside. So we have a all straw building, essentially experimenting with the possibilities of what you can do with straw as opposed to saying, well, what are we going to do with our problem? And then figuring out how it's going to get shipped up site. So all the logistics of how you build are central to thinking through the process. This is 2 weeks ago. And this is the helical piles going in. So this is what one of the helical piles looks as it drives in. They drive one of these within a couple minutes. And you'll see it. I thought they just went straight up and down. They just move them around until they get them pretty straight, and then they drive them down in. This was 2 days ago, and on Saturday I'll be driving up to the site to help lift all the pieces into place. All right, and so I'll hopefully be able to report that all of this works spectacularly. That's part of the experiment, and that's part of what we feel is our responsibility as practitioners, is not just talk about it or bemoan the challenges that are around us, but actually experiment, research, figure out what's possible, and to try to determine that future isn't set yet. It's still in our hands to make that change. And that change can actually look spectacular, can be beautiful, can be delightful, can be unexpected. And I think that's one of the powers of architecture. And I really want to thank you for the opportunity to be able to present this to you today. Thank you.
Or should we actually bring that microphone back? All right.
I'm happy to take questions.
My name is Sarah Zachman. I'm in my second year of the master's program of architecture. And towards in the beginning, when you were talking a lot more on sections, I think that's one of the areas that I struggle in beginning in my development of design. What is some advice, or what do you do in order to incorporate sections earlier in your design and create successful ones?
Two things. One, go into a space like this. Doesn't have to be this space or any other. I try to draw the section. So get used to understanding spaces, not in plan or in perspective, but as a cut, because it's an imaginary cut. You have to actually think, okay, where's that line going? Where's it going? What happens when it goes in? Does it go into that building? No, it comes out. There's glass. It goes. So you have to imagine where that's going and trace it. The second, so that's one, just get used to the practice of thinking the world through the idea of making an imaginary cut, which is at the same time the production of information and knowledge, which is what the idea of drawing is about. It's not just drawing the thing, it's actually creating new information. And the section is particularly good at doing that. Plans we're used to. Sections, because it's less normal, gives you that capacity to be a little bit more, I didn't see that before. Second is, if you're doing a digital model, print it out early and draw over it. Use the three-dimensional model as a tool early on in the process, clipping lanes fine. Print it and draw over it. So you are engaged in a process of working that's super fast, really imprecise, right? Computers are extraordinarily slow. and really precise, and push the two of them against each other. Be my recommendation.
Appreciate the talk immensely. This is very good. I have two questions, one which is easy and one which may not be. First off, what do you do your drawings in for your books? Because they're wonderful and they've been referenced a lot of times around here. And then second, a lot of the plant-based materials, big fan of. However, here in the South, we have termites. How do you foresee bringing in a lot of the biogenic materials and then basing it around our mental conditions here and the code environment that is driven by that?
Rhino, illustrated. Hand draw. Rhino, Photoshop. So it's always a kind of, it's not a linear workflow, but most of those models are Rhino, cut, detail only on one half after you set that, because you want to draw the model over the parts you don't need, and then Illustrator for the line work. Your question of code is essential, right? It's critical that every region adopts the material that's appropriate to itself. I know the Northeast region, right, where it's a question of moisture, where you go from high humidity to super cold, and you have to navigate that through insulation so that you're not getting differential moisture conditions from the outside and from the inside, because you're going to get two different lines coming because of the nature. So the answer to your question is looking locally. What works here? What are the practices that had been done pre-industrial that worked? So you can look to historical practices to find out, before we introduced modern building materials, what was used, what was really good, what was effective. Doesn't mean that you adopt the form, but you can learn from the material practices that were part of indigenous as well as local traditions. I don't have the answer for here because I haven't done work here. But I think that would be the process. We look really critically like, oh, actually, this had worked really well. Why can't we readopt that now? How does it set on the ground? How does it lift up? What are the techniques for overhang? How do we do a sun, shadow, moisture, thermal capacities? And not think about our buildings as isolated from our thermal changes, but actually playfully engaged in the world of thermal change. I'll give you a reference afterwards.
Yeah, so I was just curious about the logistics behind finding clients who are willing to try these new methods that you guys have come up with. And if there's been have you ever pitched ideas to people saying I'm really excited about this and want to try this, but they come back with, I'm not sure about that. I don't want to put the funding behind it. What if this seems kind of crazy? Just how has that been navigating? And yeah, thank you.
It's a really good question, because we grappled with this with the office, which is, if we're going to make this significant change, how are we going to do so from a business standpoint? So you have to look at it about, what are your priorities, what are your values, and how are you going to pursue it? But you also have to approach it not from a purity standpoint. In other words, this is something that's really important, and I don't talk about it here, which is there is no perfect building system, right? The gradients of better, right? So don't let perfection be the enemy of the good, is the cliche. So we made arguments for clients for a particular thing. They said, no, we can't do this. So we go, okay, given that, where is that we're going to be able to do our best practice? Where's the greatest value we can provide, right? So, and this is a case you always want to present, here's the best knowledge. This is my responsibility as the architect. I need to be, if you're a client who advocates for climate smart solutions, an institution, it's my responsibility to tell you what that building would look like, right? And then to pose the benefits and drawbacks of each of those. So we recognize that we're not pursuing work that we would have previously pursued if we don't have clients that are interested either in that, or there's different values that are being presented, and each client is different, right? These buildings, they still require metal posts in the ground. Right? They still require, so there is no perfect building system. So don't let that idea of perfection keep you from doing something that each day is going to do better and better work. Particularly at a time in which most of this is open. Most of this has not been thought through, which is why it's super exciting if you're in school going, I want to do that. I don't want to do what everyone else has done. Right?
I had a question specific to materials. So you mentioned antimicrobials being a chemical that we should avoid, but we work in a lot of us work in hospital architecture where antimicrobials are really important. Are there any natural alternatives that you know of that are being accepted or being researched?
So the question you pose is really a fundamental one, which is something's being presented on the marketplace as doing something. There's evidence behind it. Right? There's also evidence that shows that this has unintended consequences that's being presented as evidence. Which do you choose? So the first thing to do is to get those original resources, look through them, find out who the funding source is, and to determine which of the systems are you most interested in pursuing. Antimicrobials target very particular microbials, but they also don't differentiate between other ones. All right. There are natural building practices that have been used, whether it's a line-based interior finish that doesn't need antimicrobials because it already is. Right. But when we start putting polymers and paints on finishes, we now have to add something, that multi-layer thing where everything does only one thing, because the surface no longer is a breeding ground for the very thing we don't want, so we now have to put something on to kill it. Why don't we think through the building system we put in the first place? So that's my basic approach is if we're adding antimicrobials, why is that being produced now in that condition? As opposed to, I'm going to add something to fix that problem because I guarantee you it's going to create another one. So both as a research question, look at your data, look at your resources. What's it saying? Who are the sponsors? And how is it being affected? And from an architectural standpoint, why is that being added? Maybe it's because we have buildings that don't have enough daylight. Right?
Oh, hello. I'm very fascinated by the straw house. So I was wondering, since you used a combination of thatch and compressed straw, uh, was there any like fireproofing applied to the thatch? And what was like the process of testing the fireproofing for the house and the compressed straw?
So fireproofing fire is really critical because it's the one thing that everyone thinks about straw is going to light up on fire. Part of the reason I show the blowtorch onto the compressed straw is that it doesn't light on fire. Compressed straw doesn't. A lot of materials you think light on fire only light on fire in their loose, fluffy form. In a compressed form, it will char similar to mass timber, and then that outside will essentially protect the inside for structural reasons. Thatch is a little trickier because it's not compressed, right? So there are materials out there that you can put onto thatch to fire safe it, right? Because this is an experimental building, we're not putting that material on. The challenge here is trying to figure out, okay, if you do it in a building system, where is it that you have to demonstrate its capacity? So you change from being an architect to now someone that has to do performance testing, which is part and parcel of entering into this world. Had to demonstrate that you can do it. So new frameworks, for instance, had to do the fire test to be able to verify that their system works. I can now use that fire test when I file that building construction type because they've done that work, right? So a part of this is knowing, okay, what's the purpose of it? What's its goal? Is there a product out there? Is it safe? And do we need to use it given the location and classification of the building? Our primary interest in this one was the structural capacity of the building.
Hey, is
Hi. I think for some reason it's not working.
there we go.
Oh, it's good.
In your straw house, did you guys account for any ventilation or any cooling or heating systems, or like how would you incorporate that in the future?
Two different straw houses, two different approaches. Straw is a vapor open system, so we didn't want to close it down. For the straw house on the lake, it has a lined interior, which is your primary air barrier, straw, and then on the outside is a Mento 1000 or Mento 3000, which is from solid. It's essentially a vapor open membrane. So that building will move moisture, but it also meets building code. To do a project in building code in upstate New York, if it's over a certain square footage, it requires an HRV and an ERV. So this building has the one on the lake has an ERV built into it, even though, yeah. So there are proposals for doing open windows. There are other ways to do it, but we immediately go to a code that has a mechanical solution. I want a building permit. Okay. This one doesn't. All right. This one is meant to be vapor open and just vented by opening doors and windows and screens and allow that passive air to move through. It's also really small. It's not air conditioned. It's an experimental project. So it didn't have the same level of code expectations. But in general, the building codes are written to assume that you have a super airtight project that's thermally isolated. I'm not sure is always the best practice, right? Given the way I'd rather live in something that the temperature changes, and I'm used to it, something called a sweater, put them on in the winter and, shorts in the summer. I'm happy to live in different temperatures, but the code doesn't allow me to do that. So that's a challenge in terms of the way in which one practices and approaches projects.
Yeah, great presentation. Thank you so much. Question for you. As we think about a future wherein we are operating with a kind of consciousness about carbon and, embodied carbon, we think about bringing that to scale and moving the needle globally. What are the kinds of catalysts that you imagine are going to be most effective or even necessary economically, in terms of regulatory environment, socially, to motivate change and scale?
Your question already begins to point to in many ways the complexities of the answer. In other words, it's not from design alone. It's not from architectural practice alone. It requires government, it requires code, requires an entire supply chain that that moves from agriculture all the way to form and then back down again. Everything from how you do construction, how construction waste is both tracked, and how carbon is calculated. Where I'm interested right now is what I see happening is the recognition that it's not a singular issue, but there needs to be really good communication up and down the construction supply chain. So that's happening in a number of areas. The Bio-Based Materials Collective, which is a group of developers, architects, fabricators, contractors, growers, are getting together to figure out how do we actually link all of this together within the Northeast region primarily. But it's to realize that it's both local, but it also deals with kind of broader global condition. From a scale standpoint and a design standpoint, most of the work we're trying to do here is about how do we do prototypes about systems that can be standardized. It's intentionally not trying to return to a craft-based argument because that will never get to scale, both for issues of cost, but also questions of labor and capacity. So one of these two systems, one using the DuraPanels, engineered material that comes off the line, if we can figure out how to standardize that system, it allows scale. The new framework system, they're trying to scale it through the way in which they've set up their low capital model, which is really smart, socially equity based. It's also, there's another company called, there are a couple other straw-based panel systems, EcoCocoon and one, that are looking at generating millions of square feet of material at scale, be it through robotic factories that can build this stuff, because you have to be able to compete at scale and at cost to get that into the marketplace. So it's really using this as a kind of testing ground, but it also, from my standpoint, gets driven by a kind of opportunity for architects to imagine these things as not looking like just buildings that happen to use this material, but buildings and forms that actually come out of the thinking that is done in partnership with the material and the material practices that go from the grower all the way up to the fabricator and the deconstructor.
Thank you. Very interesting presentation. My question is on durability of your construction over time. You mentioned lime as a adhesive, and given that straw is has accessible sugars, that they are prone to hydrolysis in alkaline conditions. Have you tested durability over time, and what is the life of your construction look like?
Yeah. So there are two things that intertwined with that. At least there are probably more. One is every building is temporary. So there are very few exceptions, and those are within geologic time relatively limited. The pyramids, 4,000 years in a billion-year history. So we're talking about what is the time frame that we're looking at. The second is, if we look at buildings as being maintenance-free, there is no such thing. There's no such thing as a maintenance-free building. Right? So every building comes with a kind of maintenance practice. Is that maintenance practice actually built into the process? So if lime starts cracking, can you repair it, or do you have to strip it down, toss it, and put a new one on? So I'm approaching it from the standpoint of looking at these projects, looking at the history of, say, lime on straw-based systems. What works? What are the best practices? Where can I anticipate that there'll be problems down the line? Problems meaning that it'll start showing its age. Is this a problem or not? Do I actually want that question of age? In general, I think part of what I'm getting at in answering the question is to ask the shift of the kind of aesthetic condition. Often that aesthetic condition of modernism is that it needs to look as if it had never been touched by anyone. And is that actually possible? And is it a good thing? Right? In general, buildings always look like they age. Some age well. And those tend to be the buildings that are using natural materials. Buildings that are using more polymer-based materials, when they age, they look like... Okay. So that's... And you can't really repair them. Does that make sense? So it's not to ignore the question. I want to foreground it as a question about what is the framework by which we understand repair and understand durability and understand the value of time as it registers. great having all these questions.
Yeah.
Kind of piggybacking off that previous question, looking at some of the more permanent pieces of infrastructure, I'm going to use hospitals as an example. As we look at these biogenic materials, what is their ability to last, say, 100 years or be repaired in strategical ways that don't compromise the need of usabilities? Like, is this going to be a system that we can apply to these critical pieces of structure, or does it need to stay in the realm that is more flexible?
I would first ask you on. So the question you're asking is about durability and how long will these last? Are these going to be lifetime buildings? I've worked on a number of concrete-based buildings that were built not very long ago where that concrete is not going to last, is about ready to fall down. They put the wrong water in with the wrong amount of salt. When they mix the thing, we're going to have to take it down. Right? I think the assumption that natural-based building materials are going to fall apart and degrade, and modern building materials don't rust, don't collapse, don't fall apart, is where I first start. I just say, is that true? Is that binary true? And second of all, which materials are durable over the longer time, right? Straw-based buildings with lime built in Kansas in the 1880s still exist, still function perfectly, right? So the durability question is also a question of craft and how it's put together. Like, is it put together by someone who knows how the building will work? Will it adopt? So in each case, I guess I'm answering your question by wanting to think through, first of all, the binary between traditional steel concrete as permanent, which I don't think they are, and more modern or contemporary bio-based regenerative material is somehow not permanent. I actually think that line is far grayer and far more interesting to look at as a complex round, looking at the durability, looking at questions of craft, and looking at the consequences of what we're doing.
Over here, Harrison.
There.
Where you at? Here.
I'm in the worst possible spot.
All right. So my question goes back to the, it's kind of a play on the past two questions. So in many of the slides, when we were looking at the way that these unitized straw members or pieces were constructed, many of them are using kind of something more linear and all in compression. One of my question here is knowing that this construction typology has been used for literally millennia in the form of wattle and dog. Have y'all done any experiments with instead of compression with something where you have more control over the fiber layout, something like weaving and those kinds of experiments?
Not yet. So, but what you're getting at is a key point, which is we're intentionally working in compression, right? We want to be able to take straw and see if we can compress it so that it doesn't deform when you load it, which is one of the challenges of straw-based systems, is that it tends to have a non-linear compression rate. And so if you compress it, it will, anyway, so it's been looking purely at the kind of question and compression. But if you look at historical examples, the idea of plasticity, particularly in earthquake-prone regions where they're using a kind of fiber systems with a more mass-based systems in order to deal with the deflections, is really essential to try to anticipate how you would build regionally. How would you build in areas such as Japan, where they are thinking about using the kind of fiber to be able to allow plasticity to a kind of clay or earth-based building practice. So it's a different line of inquiry. It's certainly open. I mean, there's plenty of opportunities to be able to look through these. But from our standpoint, one of the things that we look to traditional building practices, not to replicate them to produce a kind of pastiche of that, but to actually look at the kind of information that's embedded, the knowledge that's embedded in that. How can that actually be pulled in, scaled up to deal with the challenges of today? whether it's compression, whether it's tension-based systems, whether it's large span, where you need to put steel in the timber-based system to allow that timber to do as much as possible. It's not about the perfection of one versus the others. Where do you use things to maximum value?
Thanks.
Thank you all.
We're done. No, there was
Yeah. This is more of a cost question. I feel like it had come up that this is purely research and research costs money. And so aside from those costs, but I guess in the next couple of third time frame in that span, do you see this sort of becoming a low cost way? And aside from, I guess, reusing materials, it's ground up construction, something like this, and using affordable housing, what would the cost difference be? Is that a factor that the research?
So I can give you one answer on cost. The helical piles are a lot cheaper than a concrete formed system that gets put into place. All right, that's why we went with it. It's also quicker cost because it's already at scale. Right? It already has a system of fabrication that's at play. Other systems, are really dependent upon the market that they fluctuate in. If you look purely at the material itself, I'll take straw, for example, that by itself has to be cheaper than an industrial process material. It's a waste material. Right now, it is cheaper if I get that thing alone, but not the systems around it. So what we have to talk about is when people say we need to scale this, you need to start building this into practices where it's much more conventional. Contractors will know about it. You basically have a learning curve. It's not that different than the transformation that occurred in the 1910s and 20s and 30s in moving from stone to concrete, right? The scale curve at a certain point, it's a struggle, and then all of a sudden it's going to be cheaper because then the fact that there's less fabric process energy, hands that go onto a material should by nature, if it weren't for tax incentives and other systems, be less expensive.
Time for one more?
Again, it was great. Great presentation. Thanks. And I appreciate your emphasis on section. Some of the students around here might ring a bell. Anyway, my question has to do with scalability and the overall carbon footprint of small scale detached structures as opposed to, let's say, urban scale structures, things like that. And so, have you looked into the overall carbon footprint of what living in small scale detached structures spread across large landscapes compared to larger scale buildings and things like that?
What you're pointing at is absolutely true, that living in dispersed, sprawled, single-family houses is far more carbon intensive than dense urban. And we knew this, and it's we debated in the office, how do we address the need to make change, of which the house in the discipline of architecture is not only a source that needs to be changed, but will continue as an economic unit in the United States for the foreseeable future, weighed against the challenges of seeming to advocate for more houses. So I'm glad you brought this up, because I didn't make that as clear, that we have some anxiety around that, and tried to foreground that in the writing of the book, that the house itself needs to be transformed, but it's not the best model by any means. Right? The second point of your question is there are already projects being built now 12-story, 14-story timber straw houses. One in Malmo, Sweden, that I think is open. There's another one that Henning Larsen is in the process of doing the site work for a very large distribution that's all a straw base using an eco-cocoon system. The scalability of this is underway, right? Actively underway for doing multi-story dense urban buildings and meet fire code. Right?
Yeah, I know about mass timber.
So mass timber without putting foam into it. I mean, so mass timber with a better building system. So the caveat around single family homes is there. We need to change that industry, but we need to do that change while at the same time recognize it has its own limitations. So thanks for bringing that up. Excellent. Thank you all.
Yeah.